In today's video, we'll start looking at particle equilibrium. This is chapter 3 of the book, and we'll talk about the first two sections of that chapter today. Let's review. A particle is an assumption about a rigid body. It's a simplification of the rigid body. So for example, we could draw a particle as this one little point here. In essence, what we're saying is that all the forces on the body have a line of action that intersect. So for example, we have force A and force B being applied to this body. And if you extend the lines of actions of both of those forces, you find that they would intersect at one point. What this means is that we can treat things that look rather complicated, like a truss that has 3 beams attached to it, in a simpler fashion. So if the lines of actions of all of those beams line up at the same point, then we could say, so it's a particle, so we need only concern ourselves with one point, namely this point where all the line of actions intersect. The second important concept to review is the concept of equilibrium. Equilibrium in essence means that whatever it is that you're worried about doesn't change with respect to time. So what it's saying is if I take the derivative of some quantity with respect to time, it's equal to 0. In the case of mechanics, what we're worried about is motion or velocity. So the concept of equilibrium in mechanics says that dv dt is equal to 0, and we recognize that that's nothing more than the acceleration of the body. If we look at Newton's second law, this means that the sum of forces, which is equal to mass times acceleration, is also equal to 0. And so we have a simple equation, which we've talked about before, which is that the sum of forces on the body is equal to 0. In chapter 2, when we added up all the forces acting on something, we had a special name for it. We called it the resultant force. So what we see is all equilibrium means is that the resultant forces on a body are equal to 0. We can extend this a bit further by recognizing that those forces are typically written in Cartesian notation. Alright, so when we write this in Cartesian notation, we write that the resultant force is the force resultant in the x direction times I, force resultant in the y direction times j, and force resultant in the z direction times k. We should recognize that to obtain this, what we really were doing is summing all the forces in the r direction. So in essence, force in the r direction x is equal to the sum of all the forces that were applied in the x direction. Force in the r direction y, or the resultant force in the y direction, is equal to all the forces in the y direction. And similarly, forces in the z is equal to the sum of forces in the z direction. What we should now recognize is that if Fr equals 0, each of these 3 terms has to be equal to 0. And so equilibrium really means that we have 3 scalar equations that have to be satisfied. The sum of forces in the x direction equals 0, the sum of forces in the y direction equals 0, and the sum of forces in the z direction equals 0. So this is actually a rather simple concept. So in essence, what we're going to do is try and get 3 equations with 3 unknowns and solve them. There's a procedure that we should use to do that. So step 1 is to draw the particle, or we could in this case call it the body. And that's simple to do because it's just a dot, it's just a point in space. Step 2 is to show all forces. So we may have a force here, which we'll call F1. We might have a force in this direction, which we would call F2. And we may have a force in this direction, which we might call F3. Step 3 is to show any angles or distances that are relevant. So for example, we might need to indicate that this angle is 30 degrees. Step 4 is to be sure that we've indicated an axis or a coordinate system on our figure. So for example, this we've done in 2 dimensions, so I may need only to draw that this is the x direction and this is the y direction. Step 5 is to write the equations of equilibrium that actually apply to the drawing. Okay? So in 2 dimensions, 2 equations, and in 3 dimensions, 3 equations. And then finally, step 6 is to solve them. Solve the equations of equilibrium. Now, sometimes we have more unknowns in equations. For example, we may have 3 unknowns in the case of a 2D problem, but we only have 3 equations that we can determine using the concept of a free body diagram and the equations of equilibrium. In this case, we need to develop more equations based on the situation that's described in the problem. One way to develop more equations is to recognize some physical constraint of the system. Another is to recognize specific types of connections or devices and utilize assumptions relevant to them. So 2 examples of devices or connections that have specific assumptions that we can apply, I'll talk about now. The first is a spring. So I'm sure you've studied springs in physics. So we have spring that's stretched to some length L. It was originally some length L naught, which means the extra length S has been added to it. And so we can write that S is L minus L naught. All springs have what we call a spring constant, or K, and we can determine the force in the spring simply by multiplying this spring constant times the extra length that's been obtained by the spring, or in the case of springs under compression, by the reduction in length of the spring. So this is in effect a new equation. So this is an extra equation that we can now use to solve problems. Another concept that we come across, or device or system that we come across quite often, is that of a rope or a cable that's wound over a pulley. So we may be pulling with some force F1 on one end of the rope and another force F2 on the other end of the rope. Because the rope is continuous and we treat the pulley as frictionless, we can actually say that F1, or the magnitude of F1, equals the magnitude of F2, which is the tension in the rope. So this again is a new equation. So let's put this into practice by kind of looking at an example. So we have the case here where we have a ring with 3 ropes attached to it. One of those ropes goes down to a crate that weighs 200 kilograms. One of those ropes goes over to another ring that's directly attached to the wall. And another of those ropes goes over to this device, which is really the center of a roller that can roll up and down on this wall. Okay? We're also told that there's a distance of 2 meters from this wall to that wall, that this particular rope is 1.5 meters long and can withstand a force of 3.5 kilonewtons maximum. Okay? And the question is, what does this distance y need to be in order for this system to support this 200 kilogram load? So let's follow our steps. Step 1 is to kind of draw the particle. So here's our particle. Step 2 is to draw the forces. So each of these ropes can carry a force. So here's one that goes in this direction. Here's one that comes straight down. Here's one that always goes straight to the left, because if this ring moves down, then this roller can move down as well to accompany it. Okay? So if we go back and label these and call this point A, this point B, and this point C, we can label these forces. So this is the force from B to A. This is the force due to the crate. And this is the force from B to C. We also need to show any angles or distances that are important. So we could note that this distance is 1.5 meters. And that obviously there's some angle here. We don't know what it is, but let's call it theta. Now we're going to indicate axes. There's x, there's y. So this is our free body diagram. Now we can write equations of equilibrium. So our first equation will be the sum of the forces in the x direction. So I have FBC, but it's pointing in the negative x direction, so it's creating a negative force. This FC force is creating no force, has no component of this force is in the x direction. FBA does have a component in the x direction. So FBA times, let's see, the cosine of theta, and you add all those up and you get 0. So FBC plus FBA times the cosine of theta equals 0. Now we do the sum of forces in the y direction. FBC has no component in the y direction, but we do have FC in the minus y direction, plus FBA and the sine of theta. So that's in the positive y direction. So if we look at here, we have a couple of unknowns. We have FBA, we have FC, FBC, and cosine theta. So we actually have 4 unknowns, but only 2 equations. So we need to write some other equations down. Well, one thing we can write down is that this force in this cable is due to the weight. So that force has to be 200 times 9.81, right, newtons. So still have 4 equations, but now we have 3 unknowns. The last thing that we'll note is that the problem says that this cord can only hold 3.5 kilonewtons max. So let's set FBA to that 3.5 kilonewtons. If you plug this information, which is in essence 2 other equations, into these equations, you can solve them. I'll leave that to you to do. The answer is theta is 34.09. The force in cable BC is 2.898 newtons. Thank you, and we'll look further at this in the next lecture.